Well, looky here. It's a fish to fry. Hey there, everybody. Welcome to episode number 517 of this here electronic engineering podcast called Amelia's Weekly Fish Fry. Brought to you by eejournal.com and written, produced, and hosted by yours truly, Amelia Dalton. This week's podcast, my friends, is a unique blend of chiplets, die-to-die interconnects, and bunch of wires. My guests are all from Eliyan, who is leading the pack when it comes to chiplet interconnect technology. Eliyan co-founder and CEO Ramin Farjadrad, co-founder and head of business and corporate development Patrick Soheili, and co-founder and VP of engineering Syrus Ziai, all join me this week for a deep dive into the world of chiplets and chiplet interconnects. Let's go. Hi, Patrick. Thank you so much for joining me.
You bet. My pleasure.
Hi, Syrus. Thank you for joining me.
Great to meet you.
And hi, Ramin. Thank you for joining me.
Likewise. Great to meet you as well.
So first off, your general focus at Eliyan is on chiplets, and particular the die-to-die interconnect challenges of these architectures. So first, can you talk about the history of your development and the bunch of wires or bow approach? Why is it so important now, and why is your particular approach an advancement over the state of the art?
Sure. Actually, this journey started about 6-7 years ago. I had another company, it's a startup company that we were growing, and we had to compete with the big guys like Broadcom and Marvell. And to stay competitive, we had to start moving to this new process, CMOS process called FinFET, which was very high performance, but at the same time very expensive. Every manufacturing mask set for that cost us several millions of dollars, and we had, let's say, 10 products. So as a company, we couldn't afford to pay for all these mask sets and so forth. At the same time, our products, the 10 products, basically composed of 2 or 3 main building blocks. So the idea back then was, why not build each of these building blocks in a separate chip, which called a chiplet, and then connect them together to build any of these 10 products. Of course, to do that, you needed a very efficient die-to-die connectivity between these chiplets. And that's what kind of triggered the idea of creating such a very efficient interface between the die-to-die were super important. And we started development in that direction for a few years. We actually turned it into a product at some point in 2019 and 20. And some people, of course, heard about it in the industry earlier. And because of some of the efficiencies that this interface had, asked me to propose it at OCP. It was the Open Compute Platform, which I did back in 2018. And it was received well. And over time, it got more support and eventually became a standard of die-to-die connectivity at OCP last year. So Bunch of Wire was the name that we picked for it at OCP.
So the chiplet trend is not new, certainly, but it does seem to be accelerating these days. What do you think is behind the surge in interest?
Basically, if you look at the semiconductor industry, it started maybe 4 or 5 decades ago. And for many years and decades, it enjoyed from something called Moore's Law. What Moore's Law gave us was every generation of process technology that happened every 2 years, gave us 2x more density in terms of transistors and functions that we can put in a certain real estate of the chip. At the same time, it gave us voltage scaling and double the speed. So every generation not only gave us twice as much density, but also 2x faster chips and gates, and also 2x lower power. This trend continued till about maybe 15, 20 years ago. The faster chips, the 2x power saving, 2x being faster, kind of started to slow down up to maybe about 10 years ago or so. But people still enjoyed the fact that they could put twice as many transistors per real estate. So by just taking the same architecture, same processor architecture, for example, x86, into a new process, they could double the performance every 2 years, which was what Moore's Law had predicted. But especially over the last decades, this 2x density per area also started to decrease, to the extent that one generation became 70% more dense, the other one 50%, and this latest one is like 30%. Instead of 2x, it's 1.3x denser. So to still get this 2x performance, people have to grow their chips. So they cannot fit the same stuff, logic functions in the same area, get twice as much compute performance. They have to grow the chip. And something that also happened, especially in the last 5 years or so, is the AI and this machine learning and high performance compute that created a lot more demand. At 2x more performance per year change into maybe 2x performance every half a year. And that also drove these chips to be really big. So it's gotten to a point that chips cannot grow any bigger and any further. So you want to build these high performance SoCs, you cannot fit them on a single monolithic chip anymore. So industry realizes that they have to build them into smaller chips, still manufacturable, but connect them together very efficiently as if they are sitting on the same chip. So this chiplet-based architectures achieve the same goal by enabling these chips to effectively grow larger and larger and not be limited by the process technology.
So, what kind of companies and applications do you see benefiting from chiplets and your approach specifically? Now, are your customers the chip companies or are they the hyperscalers and other companies that need more efficient computing? And to follow up with that, what type of relationship do you have with the manufacturing players? The foundries like TSMC, Intel, Samsung, and other big memory suppliers.
I would say eventually any company that makes chips or needs chips can benefit from the technologies that we provide or chiplet technology. Everything is eventually moving in that direction. But today, the biggest needs are companies that are building high performance compute, AI chips, machine learning chips, and so forth. It's either the companies that build them, such as Intel, AMD, NVIDIA, or companies that actually also use them, such as hyperscalers, Google, Amazon, Facebook, and so forth. So all these companies are trying to build the next generation high performance compute, next generation basically data centers that have strong AI and machine learning capabilities. So all these companies will need it. And they are the first guys to need it to build these super high performance chips. But I believe eventually more and more companies are going to move in that direction. In fact, if you look at cell phones, for example, they're not necessarily high performance compute, but for efficiency, for cost, for lowering the power and getting higher performance, they're also moving into heterogeneous designs of solutions and building systems in a package that provides higher performance at a lower power, which is key for cell phone as well. So I would say first high performance compute guys, AI guys, and then applications that need really low power and benefit from system in package high performance.
I'll interject just for a couple of other kind of additional points of clarification. Because Moore's law is slowing down, if not quite stopped yet, and we all have an insatiable desire to increase the number of processor cores or parallelism in our chips to get better and better performance so we can build bigger software models on top of them. The only way to get there is to do a chiplet or a bunch of chiplets, because you can't get that out of a single silicon. You've got the reticle size that will give you the limitation of 1200 or 820, 30 millimeters square. But if you want to put more stuff in there, you have to basically divide it into 2 or 3 or 4 and then put them all together. If you look at what AMD and Intel and a couple of other companies have done, they've also taken out the I/O part of the structure of their big chip and therefore allowed more room to put more CPUs and more parallelism into the main chip. But also, because of the I/Os are usually mixed signal, they can keep those in an older process node and then keep improving the processing core. So by separating the two, but then they have to be reconnected. And for reconnecting those, you're going to need a technology like ours to put them all back together. So the application is increasing as opposed to just being limited to a couple of 3 different players. So in whatever market you're in, as long as you're designing a chip and you have a requirement to kind of increase the number of parallel processors, if you will, and for lack of a better way, or to reconnect some of the I/O structures that you go from a homogeneous to heterogeneous architecture, you're going to need chiplets. The third one is when you want to mix and match different technologies together to come up with different SKUs of different applications. I want to be in a car and I want to do some fusion processing. Well, you've got LiDAR coming in, you've got radar coming in, you've got all kinds of stuff coming in at the same time. So you've got different technologies perhaps sitting as your core processor, and all have to be received in different, signaling schemes or even technologies for that matter. Now you want to put 130 nanometer and a 65 nanometer and a 3 nanometer chip all together. Those are all in chiplet forms, and they all have to be reconnected through the same technology again. So many, many different applications and lots of users.
That makes sense. Now, one of the benefits chiplets seem to offer is enabling integration of multiple technology processes, like you mentioned. Does this lessen everyone's dependence on the leading edge processes where TSMC dominates and actually help give more people more options, especially from US manufacturers?
Sure. I think in general, being able to mix and match chips from different manufacturers is what the chiplet movement is enabling. And as part of that, then the ability to select chips from different process nodes and different manufacturers, and even the same manufacturer at different geographies, opens that possibility up more as well. So absolutely, this is aligned with that economic reality that we all have to have in the world for supply continuity.
So Intel has promoted and gained a lot of support for the UCI standard method of chiplet interconnects. Where do you guys fit in with that initiative?
What I can say, when I presented Bow, it used a special signaling scheme, special architecture that made it very suitable for die-to-die connectivity. Make it a very efficient choice for die-to-die connectivity and the implementation of such scenario. Of course, it took a while for me to kind of preach it to the industry and so forth. And what Intel also created and called UCIe on the organic package version that it has a lot of similarities to what we had as a bunch of wires of BOW. So given that we come from that background and what we have implemented was based basically BOW was based on that. And now with small modifications, in fact, we can offer a UCIe version. In fact, what we recently tape out is going to be UCIe compatible as well. So we're going to benefit from that advantage. We would be very early to market with our solution of a UCIe solution, which offers the highest performance, highest bandwidth of the UCIe over organic at this point. So we just happen to be lucky this time that we started our company and managed to tape out this chip in 5 nanometer.
So you guys recently announced a Series A funding round of $40 million. So what does that kind of endorsement mean to you as a startup, and what kind of runway does that provide you?
So first of all, getting the investment from companies such as Intel, Micron, and so forth kind of shows that these big companies do believe in our philosophy and the fact that chiplets are important for the future. And also chiplet connectivity plays a key part in that. And we continue our work with other companies in this space, and we're getting a lot of traction from other companies as well. And our goal is to create very efficient interface for chiplets such that it simplifies everybody's job to integrate chiplets together, build the most efficient chiplets. And this is also our company motto, that we enable creation of the ultimate chiplet systems, that by enabling people to build these systems without the need of advanced packaging. Silicon interposer, as an example, provides chiplet connectivity for advanced packaging because it provides high bandwidth connectivity between chips at very low power, low latency, but it comes with a lot of negatives as well. Negatives being silicon interposer has a limited size. You cannot build a large and complex system of chiplets on it. It has low yield, high cost, and also these large silicon interposers can only be implemented or manufactured by TSMC, at least at this point. So our solution eliminates the need for advanced packaging for 90% of the applications, I would say. And that opens up people's hand to create these solutions without all these limitations that I mentioned. Patrick, do you want to add something as well on this topic? Or?
Just to complement what we talked about on your last question on the UCIe, we plan to join the UCIe consortium, Amelia, and contribute to it. And we believe, given, Ramin being the original inventor of Bow and Bow being the foundational piece of all the signaling and some of the techniques that are used in UCIe, and us having just taped out a chip in 5 nanometer as a proof of concept, as a secondary proof of concept, we think we're ahead of just about everybody out there with some very, very high performance, low power metrics that are going to be tough to find. And that's a combination of a lot of patented technologies that we've come up with, as well as some trade secrets in how to design our SerDes so that it provides the highest performance per power. As far as this question is concerned, where is that kind of $40 million taking us, and what kind of customers and how long it would last? We have, as I said, big aspirations to be involved in lots of chip making opportunities, because chiplets are going to be so dominant and so ubiquitous that just about everybody has the need to use them. And we want to be part of a standardizing body that allows everybody basically get exposure and access to it, whether we're providing chiplets or we're providing the pieces of IP that are necessary to accomplish those goals. We want to be involved in it. The $40 million is a good run rate for us to be able to prove and go to market some of our early structures. We have bigger plans for bigger chips or chiplets and bigger technologies and faster and next generation, this or that or the other, that we'll come out with over time. But for the time being, this gets us going pretty effectively.
That leads me perfectly into my last question. Where are you guys headed from here? Are you guys going to be an IP company, a chip company, something else?
We're going to Disneyland.
Okay, let's go.
Wasn't that a Super Bowl answer for some time?
It was.
So I think in 5 years, we see ourselves playing in both as a chiplet provider as well as an IP provider. And in the ecosystems that we see emerging for high performance chip designs for the next 3 to 5 years, there's just an insatiable demand for connectivity between heterogeneous chips, homogeneous chips, and between compute chips, AI chips, and memories. And these are all opportunities that there are a lot of either unsolved problems or opportunities where you can increase performance, reduce power, reduce cost, and enable a larger ecosystem by designing both the IP as well as the chiplets and the chips. So we see ourselves playing in all of those segments.
And what I can add, of course, as Syrus said, whether it's IP, whether it's chip, at the end of the day, our goal is to help the industry in this new era of chiplet solutions, because this is a new era that is trying to address a big challenge in the industry. And what drives us always is to feel that we are contributing to the success of the industry with every challenge that comes along its way. And right now, there's enough challenges. This is a new domain that everybody trying to solve different parts of it. And our expertise being in the connectivity, we will try to take a stab at that front. And we've done it in the past with different technologies that created, for example, in enterprise, we extended the bandwidth in the enterprise from 1 gig to 5 gig, for example, when people really needed to extend that bandwidth, or for automotive from 1 gig to 10 gig and beyond for autonomous cars. And now we believe this is the right timing that industry can highly benefit from chiplets and chiplet connectivity, and we hope we can make big contributions to it.
Excellent. All right. Well, it's time for your off-the-cuff question, and I think Patrick drew the short straw. So here we go, Patrick. Here's your off-the-cuff. Now, since you guys haven't been on my show before, you get the standard. So, Patrick, if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there, the restaurant is closed, what would you have?
Watermelon.
Watermelon. Interesting. Why watermelon?
Why not? It's sweet, it's watery, it's juicy, it's easy to eat, and it's found everywhere.
That's a great answer. I believe that's the first watermelon answer I've had to that question, and it is one of my favorite foods. So excellent. Well, thank you so much for joining me, you guys.
Excellent.
Nice meeting you. Thank you so much.
Very nice to meet you, Amelia. Thank you.
Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EE Journal. If you're into Twitter, you can monitor our tweets at EE Journal TFM. And don't forget, if you would like to follow my personal Twitter account, check out Amelia D 1978. And hey, if LinkedIn is more your thing, I absolutely understand. You can follow us or me on LinkedIn as well. And we have a YouTube channel, youtube.com/EE Journal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series and a slew of fish fry episodes and playlists as well. And by clicking the links below the player on this week's Fish Fryin' page, you can subscribe to this here podcast through Spotify, Podbean, or Apple Podcasts. And remember, if you'd like to further support this podcast, please leave me a review on that podcasting platform of your choice. Also, if you'd like any more information about the stories covered in today's show, just head on over to eejournal.com and look for this week's Fish Fryin' page. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's AMELIA at eejournal.com, or post a comment on our forums on eejournal. For the week of February 3rd, 2023, I'm Amelia Dalton, and you've been fried.